Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on vectors. Now in previous videos I talked about a new way of multiplying two vectors together known as the cross product. And I defined what the cross product was and I gave some geometric interpretation and we did an example. Now in this presentation I'm going to derive the formula for the cross product. Okay, so let me share my screen with you and I'll show you how it works. Okay, so just to remind ourselves, if I have two vectors, say A and B, here they're written as columns, the cross product, A crossed with B, is defined to be this whole mess here, where I, J, and K are the usual unit vectors. And in particular, the geometry is the following. This cross product gives you a new vector that is perpendicular to both the vector A and the vector B. And it's important in applications like calculating torque. Okay, so what I'm going to do is show you where this form comes from. Okay, so the aim here is to come up with a new vector that is perpendicular to both A and B. Okay, so we know how to do that because we've discussed the idea of a dot product, and this sort of links in nicely with the cross product derivation. Okay, so the aim is to find or define, if you like, a vector B, a vector C, such that the dot product of these two vectors is 0. That means they're perpendicular. And the dot product of these two vectors is 0. Okay, now let's say C is written as this triple, this sort of column vector, if you like, and using, say, these column forms and this column form here, this will give us two equations. Okay, so remember that the dot product is just of A with C is that times that plus that times that plus that times that, and the B dot C, that times that plus that times that plus that times that. So you multiply component wise and you add all the corresponding parts together. Okay, so I'm going to get two simultaneous equations out of this, these two conditions here, if you like. Right? And similarly, we'll have this. All right, so we want to solve these for C1, C2, C3. Now, in this setting, I'm assuming that the vector A and the vector B are both non-zero and they're not parallel. They're not a multiple of each other. Okay, so what I'm going to do is I'm going to eliminate the C1s. Okay, I've got two equations and three unknowns, but let's go through and try to solve it and see what happens. So if I multiply the second equation by A1 and the first equation by B1, so 2 multiplied by A1, and then I take the first equation away from the second equation, then I'm going to get an A1, B1, C there and an A1, B1, C there. When I take one away from the other, they'll disappear. Okay, so if I do that, I'll get the following. I'll get an A1, B2 there, and I'll get a B1, A2 there, and a common factor of C, 2, plus, so I'll have an A1, C A1 B3 there, A1 C3 there, a B1 A3 there. Okay. All right. So what I'm going to do now is rearrange this. I can't solve that explicitly, but what I'm going to do is rearrange it and introduce a parameter. So if I say move the C3 to the other side and then divide, I can have the following. Okay. So what I've done is taken that to the other side and then divided so that the C2 and C3 are kind of isolated on top. Okay. All right. So obviously I can't solve this, but what I can do is introduce a parameter. And I'm going to introduce the parameter lambda to be this right-hand side. You could just let lambda equal C3, but it's not quite as pretty. Okay, you could do that, but I'm not going to do that. So I'm going to say let lambda be a new parameter, which is the right-hand side here. Okay, so what does that mean? Well, if that's lambda, I can make C2 the subject, and I'll come up with an expression for C2. And of course, if that's the case, then C3 equals just lambda times this. And so from here, this is lambda, so if I take this up there, I'll get an expression for C2. Okay, and now all I really need to do is get an expression for C1. Okay, so I can get an expression for C1 from, say, equation 1. So if I take those to the other side and divide by the A1, I'll get something like this. Now I can replace C2 and C3 with these things involving the lambda. Okay, so hopefully I haven't made a mistake there. And what I'd like to do now is simplify this. Okay, so if I expand, well, first of all, I've got a common factor of lambda, right? So I can take out a common factor of lambda. Now I'll keep the negative sign out there. So that A1 is going to cancel with that A1. That A1 is going to cancel with that A1. And if I look at this, I should get some cancellation here. So oh, you know what? I've split these up. So that should be, hang on, I've put in C3 there when I should have put in C2. So let me just fix it up. That should be, I can still save it. That should be an A sub 3 and that should be an A sub 2. Okay, sorry about that. So that is now there, and that is now there. Okay. All right. So if I look at what's going to cancel, I've got negative B1, A2, A3 lambda, and a positive B1, A2, A3 lambda. So sort of this term and this term is going to cancel out. So what are we left with? We're left with A3, B2, minus A2, B3. And of course I can take off the negative sign there. Okay, so there's an expression for C3, there's an expression for C2, and there's an expression for C1. Now this is true for every lambda. Okay, so we actually get a line for our solution. All right, so let me just write that down now. All right, so basically I'm taking out the common factor of lambda and writing these as a column vector. So it's going to be A2 B3 minus A3 B2, B1 A3 minus A1 B3, and A1 B2 minus A2 B1. Okay. So let's just compare that with what we've got in here. Okay, so that's, yep. If I, just distribute the negative sign in there, I get that, and I've got that. Okay. Now, this, to say this is, I guess this is a form of a line rather than a vector. So let's just keep it real simple and take lambda equals 1 to get the cross product form given here. Okay, so that is where the cross product comes from. It comes from a geometric requirement, if you like, that the new vector has to be perpendicular to both the A vector and the B vector, and we would denote this C vector to be the cross product. Okay. All right. So a couple of properties of the cross product. Firstly, if I take the cross product of a vector with itself, I get 0. Okay, why is that true? Well, just perhaps you can just use this formula and A1 and B1 are going to be the same, A2 and B2 are going to be the same, and A3 and B3 are going to be the same. So you're going to get cancellation there, and there. You're going to get the 0. So that's the 0 vector. Okay. Secondly, order is important with the cross product. The cross product doesn't commute in the sense that A times B doesn't necessarily equal B times A. And in fact, they're the negatives of each other. So the important thing is order is important with the cross product. If I have a scalar or a number, lambda, well, I can move that around and it doesn't affect the answer in the cross product. And finally, here's a distributive law for the cross product. Okay, it doesn't matter if I add these two vectors together first and then do the cross product there, or if I take the cross product separately, preserving the order, and then add them together, you should get the same answer. Okay, so if you want a nice exercise, just try proving these from the definition of the cross product. Okay. Okay, so I promised that I'd derive the cross product, and I have, and it's all based on geometry, and the definition of the cross product has to be such that the dot product of the new vector, whatever it is 0 with both the A vector and the B vector, the perpendicular requirement. Okay, so that's a little bit on the derivation of the cross product. In future videos, I'll be looking at some applications of the cross product with regards to area and volume, and we'll look at the scalar triple product. So hopefully you can join me for those presentations. If you have any questions, any comments, put them in the comment section. Thanks for watching, and hope you can join me for the next presentation. See you.